in today's lesson, we're going to continue on with more hydrocarbons and look at a few different types. One that form ring structures called cyclic hydrocarbons. We'll also look at aromatic hydrocarbons and also look at things called isomers. So the nice thing about cyclic hydrocarbons, because we're going to start with them first, all of the naming rules that we've seen so far with respect to alkanes, alkenes, alkynes, any of those rules with the naming, with the prefixes, with the suffixes, with the numbering, all of those rules apply. But there are a couple of changes that you make to the naming. So the first step is your base chain or your main chain is going to be the length of the cyclic structure only. If there are branches on that cyclic structure, the branches are not counted. They're just treated separately as branches. The second thing you need to do is add another prefix in front of the previous prefix. You add the prefix cyclo to the beginning of the name. Other than that, everything else works the same way. So let's look at some examples of how these are represented. When we represent cyclic structures, we use line diagrams for those base chains. It's a lot easier, it's less cluttered, you don't have to put in all of the atoms. So here are 4 examples: cyclopropane, cyclobutane, cyclopentane, and cyclohexane. When you look at the structures, everywhere where there's a point, where 2 lines meet, that's where a carbon is. So this has 1, 2, 3 carbons. That's why we see prop being used. Cyclo, because it's a ring, it's all joined in a shape. And then A and E for all single bonds. In this diagram, you can see there's only one line joining each point. One line here means one bond. If we wanted to expand this one, just for reference, it would look like this: CH2, CH2, and CH2. So when they're drawn with line diagrams, it looks a little bit neater, easier to draw and refer to instead of putting all those in. Why do these carbons only have 2 hydrogens attached to them? Remember, carbon can have 4 bonds. So this carbon has 2 bonds around it, and then it has 2 hydrogens around it. If we look at the other ones, we can see there's a square here. There's 4 points to a square, and you could number any way you wanted around here. I just went clockwise. Bute is 4 carbons. That's why we've got bute in there. Cyclo for the ring, A and E for single bonds, and so on. And then you can see pentagon we know is 5, so you have pentane, hexagon, hexane, and so on. So let's try doing some naming and drawing with the cyclic hydrocarbons. And hopefully you'll see that overall they're pretty straightforward. So if you have branches or a double bond in your ring structure, you're going to have to make sure you follow the same numbering rules. You want to make sure the double bonds have the lowest numbers possible, as well as the branches. If you have double bond and branches, give the double bond the lowest number first, followed by the branches. When you number on a ring structure, you can go clockwise or counterclockwise. It doesn't matter, but you have to make sure that you give the lowest numbers possible. So if I were numbering this first structure here, I would go 1, 2, 3, 4, and 5. I could have also gone counterclockwise and gone 1, 2, 3, 4, 5. I usually like to stick with clockwise if there's an option, just because I'm used to seeing it that way. Why did I do 1, 2 like this? This is carbon 1, this is 2. So where the double bond is between carbons 1 and 2. Those are low numbers. If you counted like this is not correct. When you look, yes, the double bond starts on number 1, But as you go around 2, 3, 4, 5, if you number it like this, it would be between number 1 and number 5, which are high numbers. We don't want that. We want number 1 and number 2. So once we've done that, then we can see there's no branches or anything else like that stuck to it. We can start to name it. So it's a ring structure. So we use cyclo, pent for 5. And then a double bond is ENE. You can put the number 1 in or leave it out. So this is cyclopentene. If you think you've got the general idea, you can pause the video and try and name these two, and then check back and we'll walk through the answer for these ones together. If you're ready to check these ones, let's take a look. Here we've got a square shape, so 4 carbons in the ring. Now we've got a couple of branches. You can see that they come off, but the ring makes up the main chain here. So I need to make sure when I number my branches, they're the lowest numbers possible. So I'm going to start here. 1, 2, 3, 4. I've got 4. Next, I'm going to look at anything else with double bond, triple bond, nothing fancy like that, so I could start to put the name together. Branches still go out front of the name, so I've got branches on number 1 and number 2. They're both methyls, so I'm going to put dimethyl. Then I'm going to put in the cyclo prefix, and then my main chain. So this one is 1,2-dimethyl cyclobutane. Let's try one more. Again, if you haven't tried one yet, you might want to try this one first before taking a look at the answer. So if we're numbering this one, in the last example, there's a double bond, and 2 branches. Double bond needs the lowest numbers first. So I would number 1, 2, and then continue around like this. That way my double bonds between 1 and 2, and then my branches are at 3 and 4. If I had gone counterclockwise, I would end up with my branches at 5 and 6, which would have been too high. So let's name this one down here. So branches first, 3, 4, both are methyl, so we put dimethyl. Cyclo for the ring, 6-membered ring, so hex. And here we put the double bond in, so we need ene. So 3,4-dimethylcyclohexene. Next, let's take some practice with drawing. And you can try these ones out on your own before we take a look at some answers. So I would try these two, pause them, video, try them out, and then we'll take a look at the answers next. All right, let's walk through these ones. So for part A, I've got 1,2-diethylcyclobutane. So whenever I see cyclo, I always like to draw the ring first. Cyclo in bute, I know I need my square shape. So I put that in. And then I need ethyl branches at 1 and 2. You could put number 1 and 2 anywhere you want. I'll just make this one 1 and this one 2. So I need an ethyl here, and then I need an ethyl here. You can also draw these all as line diagrams. You don't need to have expanded diagrams for the branches. So if you did want to do this as a line diagram, you would do your ring and then draw lines showing that bent shape for the branches. 1 carbon, 2 carbons, 1 carbon, 2 carbons, like that. Either one is fine. Now let's try B. So B is 2-methylcyclopent 1,3-diene. A little bit more going on. So I see cyclopent, that's what I'm going to start off with. So I know I need to make a pentagon. Okay, there's my pentagon. I need to put a double bond at 1 and 3. So 2 here, a diene means 2 double bonds. So again, you could start number 1 wherever you like. I'm just going to count it from here. So 1, 2, 3, 4, 5. But again, if you start at the top and go around, it doesn't matter. We're just rotating. So double bond starting at 1, it's going to go to 2. And then a double bond starting at 3, it's going to go to 4. And then I need to put a methyl on carbon 2. So it's going to go like this. Again, if you wanted to just do the line diagram, everything would look the same, except you just put a line up there, and that would imply a methyl group. So either one's fine. Next, we're going to move on to something called isomers. So what are isomers? There's a couple different types of isomers. We're going to start off with structural isomers. These are compounds that have the same molecular formula, but when you actually look at their structures, they have different structures and different names because of it. So we're going to start off with a really simple one to give you an idea. Draw and name all the structural isomers of butane, and butane has the formula C4H10. So I'm already giving you a hint that one of them is butane, just to get you thinking. So butane, we know, has 4 carbons, 10 hydrogens. Let's prove it. Butane is a 4-carbon alkane. So all single bonds, no branches here. When we look at this structure, 1, 2, 3, 4, 4 carbons, 3, 5, 7, 10 hydrogens. So it fits that molecular formula. Is there another way, though, that we could rearrange the atoms so that they still have the same number of carbons and hydrogens, but when we go to name it, it's going to be something else? So if you want to give it a try and write down a few sketches, pause and give that a shot. If you're not quite sure, we'll take a look at one option here. So an isomer has to have a different structural arrangement. If we put 4 in a row, it's always going to be butane. So what if we decided to put 3 carbons in a row? And sometimes it's easier just to start off with the expanded diagrams if you're not sure. So what if I did 1, 2, 3, and instead of having 4 in a row on the end, what if I had a branch here? That would make my 4 carbons, but let's see how many hydrogens would be attached to it. So here I would need 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That works. So if we were to put in all of those hydrogens now, that follows all of our bonding rules. The carbon has 4 hydrogens around it. This would be an isomer of butane. But how would we name it? This is the main chain. So when we go to number it, we would go 1, 2, 3. And up here we have a branch. So if we were to name this compound, we would take our branch, 1 carbon, which is methyl. It's on number 2. And then we would put our long chain, 1, 2, 3 is propane. So this molecule is 2-methylpropane. It has the same number of carbons and hydrogens as we have over here. This is butane. But when you look at them, you can see structurally they're different. And because of that, they have different names. So this is a simple example of a structural isomer. Same number of carbons and hydrogens, so same number of atoms, but different structural arrangements, and therefore different names. You can have structural isomers with other elements as well. It's not just limited to carbon and hydrogen, but because we haven't learned any of the other structures of the other groups in organic chemistry yet, that's why we're not seeing it. But you could have some with carbon, hydrogen, oxygen, nitrogen, whatever you're dealing with. You can definitely have others. Now, there are some helpful hints when you're dealing with structural isomers. If you're given a molecular formula like this one up here, it's actually giving you some information. So you may have noticed from some of your reading, if you're given a molecular formula from your hydrocarbons, it can tell you which family they belong to. So if you see a formula that follows this pattern, a certain number of carbons, and then when we look at the number of hydrogens, it's double the amount of carbons plus 2. This is going to fall in the alkane family. So a good example of this would be exactly what we see up here. C4, so N is equal to 4, and the H's would be 2 times 4, which is 8, plus 2, which is 10. So you can see, okay, it's falling in alkane where you get the butane. If you see a formula, CnH2n, so twice as many hydrogens compared to carbons, oops, it's going to be an alkene most of the time. Okay, if it's just straight chain. These are if they're straight chains. I forgot to mention that. Straight chain, or even some with some branches, but not mixed groups. Then we've got CnH2n, but this time minus 2. If you see a molecular formula with that pattern, it means you're probably dealing something with an alkyne. So it's not a hard rule, but this is a helpful trick if you're doing some isomer work. So let's take a look at a question with isomers and see if you can practice drawing some. So draw all isomers that have the formula C5H10. There are quite a few that fit into this category, but we can look at this to help us get started. So we might be dealing with one type of molecule or more, but this is going to help us get started. 5 carbons and 10 hydrogens. So which of the 3 patterns that we just went through up above would it fit into? Would it be alkane, alkene, or alkyne? Hopefully you can see that it follows this one here. Twice as many hydrogens as there are carbons. So what that means is some of the isomers might be alkenes, and that would be a good place to start. There are quite a few here, more than 10, that fit this one. But let's see if you can pause the video and try and maybe draw 2 or 3. That would be a good start for where we're at right now. If you haven't done a lot of hydrocarbon practice up to this point, this is going to be really hard because you have to understand how things bond and where the carbons and hydrogens go to be able to work with isomers at this point. So see if you can draw a few, then I'll show you a couple together, and then we'll move on. So if this is dealing with an alkene, and we've got 5 carbons, why not start off with one that has 5 carbons just in a chain? So what if I put my double bond on the first carbon? If I name this one 1, 2, 3, 4, 5, this would be pentene. Naming what you draw is always a good idea because then you know for sure if you have something that's different or the same. As long as you take a step back and follow the rules, you'll know. What if we did another one with a double bond? But what if the double bond wasn't between 1 and 2? What if it was between 2 and 3? Then it would look like this. And that's okay. Even a small change by one position for the double bond changes the molecule structure slightly. The name is also going to change. We know this is pent. 1, 2, 3, 4, 5. The double bond is on number 2. So this is called pent-2-ene. So you can see the name is different, even just slightly different, but that makes it a different compound. Does it have 5 carbons and 10 hydrogens? Yep, if you count them all up, you'll find that they're all there, but it's a slightly different arrangement. Then you can start working through different options. Well, what if I had double bond on the first position, but what if I decided to throw in a branch? What if I did something like this? What would happen? Do I still have 5 carbons and 10 hydrogens? Definitely. 1, 2, 3, 4, 5. There's 5 hydrogens and another 5 over here, so 10, so that works. But when I go and name this one, 1, 2, 3, 4, I've got a methyl on number 2. I've got a 4 carbon base chain with a double bond on number 1. So this is called butene. So 2-methylbutene. This is another example of structural isomer. Again, you can start to see by playing around with the chain length where you have double bonds, anything like that starts to affect the name and the structure. I'll give you one more hint with 1, and then part of your homework will be to go back and see if you can draw some more. One that also falls in this category, which is a little bit sneaky, would be this structure here, cyclopentane. How do you know it fits this structure? Well, this is where you would actually want to draw it out with some atoms. So, if we draw it out with the atoms written in, which again, a little more cluttered, but here it serves its purpose. We have 1, 2, 3, 4, 5. 5 carbons, 2, 4, 6, 8, 10. 10 hydrogens. It fits that molecular formula. But here you can see the arrangement is quite different. So, in the lesson folder, you'll find a document that says all of the isomers of C5H10. Try and draw a few more on your own, and then take a look at what some of the other options are. What are some other types of isomers? There's another type called a geometric isomer. These are compounds that differ in their position, but it has to do with how they are arranged around a carbon-carbon double bond. So we're dealing with alkenes here. They're called cis isomers or trans isomers. So why does this happen? When we look at atoms that are joined to double bonds, so they would be joined to those bonds there, they get fixed in that location. You can't disturb a double bond. There's no bond rotation. It kind of locks them in that position or that orientation. So depending on where they're attached and on which side of the double bond, you get different shapes take on appearance to the molecules. So how does this work? Let's look at an example with but2-ene. So the way we've been drawing alkenes so far looks like this. Straight chain, not really showing any of the bonds in the correct geometry. But what we're interested is looking at these carbons here, the ones that share the double bond. What's attached to each of them? They have one carbon with hydrogens and another hydrogen. How are they arranged around that double bond? So what we're going to do is expand the diagrams around those atoms only. Keep these two ends condensed, but we're going to expand the geometry around here. So let's look at those diagrams. If we were to expand them around where the double bond is, you can see here's the carbon. We'll number them for reference. 1, 2, 3, and 4. 1, 2, 3, and 4. This could be one way where they're going downwards, or 1, 2, 3, 4. If it's helpful, we can also highlight along those carbons just to see how the molecule is going to look in terms of where the carbons are joined. So hopefully, even just by looking visually at those carbons, you can see one kind of zigzags and one is going and then up and down. The orientation around the double bonds is different. You can also start thinking a little bit about VSEPR here. Around these carbons, you have 1, 2, 3 electron groups. 1, 2, 3. Same over here, 1, 2, 3, 1, 2, 3. So around these carbons here, for both of these, you have trigonal planar arrangement. So in here, you've got your bond angle 120, and then 120, and then 120. That's why they're oriented in that particular direction. So what's the difference between the two? Essentially what you want to do is imagine if I were to kind of cut along where the double bond is, where are the different sides of my molecule pointing? This one over here, I can see one side up and one side down. This one is called the trans isomer, where my chain is on two different sides. Over here, if I look where my double bond is, I've got two parts of my chain pointing on the same side. This one's called the cis isomer. That's where some of the naming comes in. Two different sides means trans, or opposite sides. Cis, two on the same side. Cis for same. How does that change the naming? Not too much. We just have to add on an additional prefix. So here it's still but-2-ene, but when we go and name the compound, this is called trans but-2-ene. And over here, cis but-2-ene. So if you do see isomers with names trans and cis and you're asked to draw them, you have to draw them in particular orientations. Conversely, if you're seeing a structure where there's double bond and you see that there's a particular arrangement, you need to name them with the cis and trans. Where have you seen some of this actually come into play in real life? If you have some time, there's some additional notes you can read through on this topic. Cis and trans fats. Yes, that change in the name for a fat, trans fat, everyone hears about them, they're bad. It literally comes down to how carbon atoms are arranged around a double bond in those fatty chains. Trans fats are the bad ones. So the name trans fats comes down to how the carbons are oriented around that double bond. Why does that happen? They take on properties of saturated fats. We know saturated fats aren't good. So by changing the shape of the molecule, it starts changing the properties, and then there's the consequences. So if you're interested in reading a bit more on the chemistry of that, take a look, and hopefully that gives you a little glimpse into some food chemistry that pops up in this particular area of our course. All right, last topic for today's lesson. What happens when you have aromatic compounds? So, aromatic compounds are a little bit different. They're still hydrocarbons, but they're based on a molecule called benzene. Benzene has the molecular formula C6H6, and it's arranged in a cyclic structure. When we look at benzene, here's one representation of benzene. It has 3 alternating double bonds. If we were to number the carbons going around, this is 1, 2, 3, 4, 5, 6. You would have double bonds at position 1, 3, and 5. It, however, has a resonance structure. Resonance structure looks like this. Same positions for the carbon, but look at where the double bonds start. 2, 4, and 6. And we can highlight this, if you like, to see the difference. Double bond starts at 1, 3, and 5. With the resonance structure, it starts at 2, 4, 6. So odd numbers, even numbers. What ends up happening is the double bonds, the electrons in those double bonds actually resonate or alternate back and forth between those two forms. So when drawing benzene, you could draw it this way, you could draw it this way, or because the double bonds rotate around within that ring structure, instead, this is one way you can draw the benzene ring. This is often a lot easier because you don't have to worry about doing alternating double bonds. Sometimes they even call these double bonds not really double bonds. They're kind of like a 1.5 bond, because half of the time they spend them in these positions and half of the time they spend in this position. So sometimes you might say the bonds in benzene they refer to as 1.5 bonds because those electrons move around. So to show that they move, they put that circle in the middle. How does the naming and drawing work? There's 2 different ways to approach it. Sometimes benzene is the main chain, and there's little branches that come off at different points. Or sometimes you can even have benzene as a branch, which is different. So we're going to take a look at both and then try out some problems. So first, let's look at the rules for benzene as a main chain. First thing you're going to do, number the carbons in the ring starting with any branches or groups that are attached. That's exactly the same idea as your cyclic structures. So give the lowest numbers to the branches or groups that are attached. You want to name the branches with position numbers, but then the ending here, you're just going to use the name benzene. So you don't count around and use the same prefixes. When it's aromatic, use benzene. What if benzene isn't the base chain? What if it's a branch? This time, you're going to name the hydrocarbon as you previously learned, or whatever structure you're dealing with. But the benzene has a special branch name. It's called phenyl. So that YL there tells you it's a branch, just like methyl, ethyl, propyl, and the other ones we've seen. But phenyl is being used here. So let's try out a couple of problems, and then hopefully you'll feel more comfortable naming and drawing these ones. So let's look at this first structure here. I see benzene in here, so I know it's aromatic, but I have a hydrocarbon chain. So I have to decide, is it the main chain or is the benzene a branch? The easiest way to do this is look at the longest hydrocarbon chain attached. Since there's only one here, I'm going to count it. 1, 2, 3, 4, 5, 6, 7, 8. The chain is 8 carbons long. Benzene ring is only 6 carbons long. So which one is longer? My carbon chain here is longer. If your carbon chain is longer, that means this is going to act like a branch. If the chain that's attached was less than 6, then the benzene would be the main part of the chain and this would be a branch. So look at the length of the chain. If the chain is longer than 6, you go with it as a branch, and if not, it's the main chain. So other than that, the naming rules are the same. No double bonds, triple bonds in here to worry about. So this is an alkane chain. I have a branch at number 3. So 3 goes up front. Then I'm going to put my dash. Then I'm going to write the branch name, which is phenyl. Then I've got 8 carbons, all single bonds. So this is 3-phenyl octane. So now that you see how this one works, let's take a look at another example. Next up, we've got benzene ring again, and we've got a couple of smaller chains joined. This is 1 carbon long, and this is 1 carbon long here. So these are both shorter than 6, so these have to be branches. So this is a branch, and this is a branch. Nothing else going on. I want to number my branches the lowest possible, so I'm going to give them 1 and 2, and just note my numbers around 6. When I go and name this, I'm going to get my 2 branches first, 1, 2. They're both methyl, so dimethyl. And since benzene is the main part of the chain here, it's going to be called benzene on the end. So 1,2-dimethylbenzene. Now that we've done 2, pause the video and see if you can do the last example. Decide whether benzene's the main chain or a branch, and see if you can name it. Taking a look here, we're going to count our chain. 1, 2, 3, 4, 5, 6, 7. I'm numbering left to right because there's a double bond here, and I have a branch at number 2. 7 is longer than 6, so this is going to be a branch. Now I can start to put my name together. Branch first, so 2-phenyl. Then I have 7-hept. D and E for double bond, and it's at number 1, so I can just write heptene. So 2-phenyl-heptene. Hopefully that gives you a taste of how some of the names and structures work together. Now that we've done those, why don't you give some a shot where you're drawing? Even though we haven't practiced these, I think based on what we just did, you'll be able to figure them out. So pause the video, try them out, and we'll take a look at the answers. All right, here we go. When I see the name, it ends in benzene, so I know benzene's going to be my main structure. 1,3-dimethylbenzene means benzene's the main chain, and I've got some branches. Branches are at 1 and 3. You could start numbering anywhere you want. It'll automatically become number 1. So let's say I put 1 here. 1, 2, 3, 4, 5, 6. That means my other methyl has to go down here. So there's my structure for 1,3-dimethylbenzene. Next, 2-phenyl-hex-2-ene. I see here phenyl is a branch. I've got a 6-carbon chain, so I'm going to draw that first. CH3, C, double bond. I put that in, there's 6. And I have to put my branch on here, which is why I left that open, so I can put my branch in. Point it down, point it up, doesn't matter. So, hopefully that helps you learn a little bit more about some other types of hydrocarbons and introduces the idea of isomers.